In this episode, we want to explore how early natural language processing worked before the era of neural networks. From simple bag-of-word systems to statistical weighting like TF-IDF, IDF, and finally to topic models such as LDA.
It's a truly foundational journey. When you look back, these early methods, even though they're built on pretty simple statistics and linear algebra, they really set the blueprint for how machines first began to perceive and measure our language.
And they're still running under the hood in a lot of places today, right?
Absolutely. They're still incredibly effective for certain applications.
I think a lot of people who are familiar with modern tools, say large language models, sometimes forget the incredibly difficult conceptual work that had to come first.
Exactly.
I mean, the core problem before you even write a single line of code was just figuring out how do you quantify something as messy and subjective as human text?
That's the question. How do you bridge that gap between abstract communication and just concrete numbers?
So today, we're going back to that starting line. We're looking at how we built the very first numerical representations of text, starting with the most intuitive but also maybe the most flawed approach, the bag of words model.
It really is like turning a complex document in just a simple shopping bag full of items. And we really need to understand what that let us do and what it fundamentally missed.
All right, so let's start there. The absolute first step is turning language into data a machine can actually process. What was that first conceptual leap that let researchers take a paragraph of text and turn it into a string of numbers?
The core idea, which really underpins almost all of classical NLP, is something called the vector space model.
Okay.
The idea is actually quite elegant. We just convert every single document into a vector, which is essentially just a long list of numbers.
And in the early days, those numbers, those features, were just the words themselves.
They were. And the first, and I would say most influential way of creating those vectors was the bag of words model, or BoW. You often see it called the sparse bag of words vector.
The name itself, bag of words, is so important for understanding both its power and its limitations, isn't it?
It is. The term bag is the key analogy. In a bag, what's inside matters, but the order you put things in or take them out, that doesn't matter at all.
I think a good way to picture this is with a document term matrix. Imagine a giant spreadsheet. Every single unique word in your entire library, your whole corpus, is a row.
And every document you have is a column?
So if your library has, say, 50,000 unique words, then every document becomes a vector with 50,000 dimensions.
That's spot on. And the value in each cell at the intersection of a word and a document tells you something about that word's presence in that specific document. That matrix structure was really the computational bedrock of the era.
Let's stick with that bag analogy, because it immediately highlights a huge flaw. If I say the dog bit the man, or I switch it to the man bit the dog.
Same exact words.
Exactly. The bag of words is identical, so the resulting vector is identical.
Precisely. The model captures which words are there and how many times they appear, but it throws away all word order, all grammar, what linguists call syntax. You lose that subject-object relationship completely.
Which is why these early models would have struggled with something like sentiment analysis. It couldn't tell the difference between not bad and just bad.
Right. But even with that massive limitation, it was a huge breakthrough. Why? What problem did it solve that made it so essential?
It solved the problem of scale, I imagine.
It solved quantification and scalability. Before BoW, trying to analyze and index a large collection of text was this monumental manual task.
You had people physically reading and tagging documents.
Exactly. Researchers in the 50s and 60s, people working in information retrieval, they needed an automatic, objective way to categorize and find documents. BoW gave them a numerical basis for comparison.
So in its simplest form, what numbers are actually going into those matrix cells?
In the most basic version, you're just using the raw term frequency, literally counting how many times a unique word shows up in a document.
But you could even go simpler than that, couldn't you?
You could. The absolute simplest form, which was often used as a baseline, is just binary BoW. If a word appears at least once, the value is a 1. If it's not there, it's a 0, a simple on-off switch.
So if I'm a researcher with 500,000 historical legal documents, and I want to find everything related to contract law, the computer doesn't need to understand what a contract is.
Not at all.
It just needs to find the documents where the words contract and law have high frequency counts.
That's it. It allowed these early systems to automatically classify documents based on word frequency. But that reliance on simple counts reveals another big problem, beyond just the lack of syntax.
And that's the vector itself.
Yes, the vectors are computationally difficult. because they are what we call high-dimensional and exceptionally sparse.
Sparse just means mostly zeros. Right.
Mostly zeros. Think about it. If your vocabulary has 100,000 unique terms, every document is represented by a vector with 100,000 dimensions. But a typical document might only use a few hundred unique words.
So over 99% of that vector is just filled with zeros.
Right. And that high dimensionality and extreme sparsity made tasks like calculating the similarity between two documents, which involves a lot of math, incredibly inefficient. You're wasting so much time multiplying and adding thousands and thousands of zeros.
You're carrying around all this extra weight that contains no actual information. Okay, so we've got a system that's great for quantification, but it ignores grammar and it's computationally inefficient. What about the meaning of the words themselves? Semantics.
That's probably the most critical limitation, and it's what drove the next 20 years of research. BoW treats every word as a completely separate, independent thing.
So if one document uses the word automobile 10 times and another one uses the word car 10 times,
the BoW model sees zero similarity between them based on those words. Automobile and car are just two completely separate dimensions in that giant matrix.
so it has no way of knowing that car and automobile are synonyms.
Not at all. This is the synonymy problem. And you have the flip side too, the polystemy problem.
A single word having multiple meanings.
Exactly. A word like bank. It could be a river bank or a financial institution. Since BoW only has one single count for the word bank, that vector becomes a kind of blend, an average of all its possible meanings. You lose all the specific context.
And that's a huge practical problem. If I'm building a search engine and someone searches for a financial bank, my BoW model is just as likely to pull up documents about geography as it is about savings accounts.
Which immediately led researchers to the next big question. If we're stuck counting words, how can we at least make the important words, the rare words that carry specific meaning, stand out from the common words that carry almost no meaning?
And that necessity is what leads us to the most successful statistical weighting system in the history of information retrieval.
Right. It brings us to term frequency inverse document frequency, or TF-IDF. This is where we move from just simple counting to intelligent weighting.
And TF-IDF is such an elegant solution because it directly attacks that core weakness of bag of words, the idea that every word is equally important.
The intuition is that the best word to describe a document is one that is both frequent in that specific document, but also infrequent across the entire collection of documents.
I love that idea. You're not just looking at the document in isolation anymore. You're comparing it against the whole library, the entire corpus.
Exactly.
So why is a word like the a bad descriptor for a paper on particle physics?
Oh.
Because the is in every document about everything. It tells you nothing.
Precisely. Words like a, is, and the, what we call stop words, are essential for grammar, but they're useless for telling you what a document is about. TF-IDF formalizes this idea of discriminative power.
And it does this by calculating a score for every word by combining two parts: term frequency, TF, and inverse document frequency, IDF.
Let's start with the simpler one, term frequency.
Okay, TF.
TF is just what we've been talking about, how often a term shows up in the current document. If galaxy appears 20 times, its raw TF is 20. But there's a problem there. Longer documents will naturally have higher counts for everything.
Which creates an unfair bias, so you have to normalize it somehow.
Right. Instead of the raw count, you might divide the term's count by the total number of words in the document. That way you can compare a short, focused document and a long, rambling one more fairly.
So TF handles the importance of a word inside a single document. But the really clever part, the part that uses the whole library, is the inverse document frequency, the IDF.
IDF is what measures how rare or common a word is across the entire collection. It's calculated by taking the total number of documents, dividing that by the number of documents that contain the word, and then, this is the crucial step, taking the logarithm of that result.
The logarithm. Why the logarithm? I think that's a key detail that people often gloss over.
It's so important. It addresses a linguistic pattern called Zipf's law. Basically, it says that in any large collection of text, a very small number of words like the occur an incredible number of times, and most words occur very, very rarely. The distribution is extremely skewed.
So if you didn't use the logarithm, the IDF score for a word that appears in just one document out of a million would be, well, 1,000,000.
Exactly. An astronomically high number. And that one value would completely dominate and drown out the influence of every other meaningful word in that document's vector.
But the logarithm tames that huge range. It compresses it.
It compresses it into a manageable scale. It dampens the penalty for common words and gives a stable, meaningful boost to the rare, important ones. It brings that skewed distribution under control.
So let's take an example. In a huge collection of documents, a word like algorithm might appear in a few thousand of them, but a word like transformer in the NLP context would appear in far fewer.
So the IDF score for transformer will be significantly higher.
And then when you multiply that high IDF score by its local term frequency, say transformer appears 50 times in one specific paper, you get a very high final TF-IDF weight.
The system has correctly identified transformer as a highly relevant and descriptive term for that document's topic.
So how did this change things in practice for early information retrieval, for example?
It gave them the first really effective ranking system. Before TF-IDF, search was pretty crude. With it, they could score a document's relevance to a query. A user searches for 3 words. The system calculates the combined TF-IDF score for those words in every document and instantly ranks the results.
This must have been the engine that drove the first generation of usable search and things like spam filters, too.
Oh, absolutely. Think about spam. Spam messages often use very specific words like free, winner, guarantee that are common within spam, but pretty rare across all of your normal, legitimate emails. TF-IDF naturally gives high weights to those words,
Making them perfect features to train a classifier to spot spam. It's robust, fast, and really mathematically elegant.
It is. But even with this fantastic weighting system, we still haven't solved the core semantic problem of bag of words, have we?
Not at all. It's still a sparse vector, it still doesn't understand syntax, and it still treats car and automobile as totally separate things.
We've optimized the counting, but we haven't actually moved into conceptual understanding.
And that's the next big intellectual hurdle. If our models still don't get that doctor and physician are related, we need a method that can somehow infer that connection automatically. We need to go from counting words to discovering underlying meaning.
Right, because that failure to handle synonyms meant that search recall was often terrible. A perfect document could exist, but if it used a synonym the user didn't think of, it would be completely missed.
So this pushed researchers to try and find latent structure, hidden semantic structure.
And the first major attempt to do this mathematically was Latent Semantic Analysis, or LSA. In search, you'll often hear it called Latent Semantic Indexing, or LSI.
This is where we really leave simple counting behind and get into some heavy-duty linear algebra.
It was a radical leap because LSA was one of the first models to explicitly say that words are not independent. It operates on the principle that words that appear in similar contexts in similar groups of documents must be related in meaning.
That's the distributional hypothesis, right? Words that show up in the same environments tend to mean similar things.
That's the one. So if car and truck both frequently appear in documents about transportation, even if they never show up in the exact same sentence, LSA should be able to pick up on that pattern across the entire corpus.
And the mathematical tool it uses to do this is called singular value decomposition, or SVD.
SVD. You take your huge, sparse document term matrix, the one we built and weighted with TF-IDF, and you basically factorize it. You break it down.
SVD is a very abstract concept. What's the intuition for what it's actually doing to the data?
Think of it like finding the main axis of variation in your data. SVD breaks the matrix down into 3 simpler ones. One that relates documents to topics, one that shows the strength of those topics, and one that relates terms to those same topics.
And the real magic, the semantic part, happens when you don't keep all of it. You truncate it.
Exactly. This is the rank reduction step. Your initial matrix might have 100,000 dimensions and it's full of noise. So you decide to keep only the top, say, 300 or 500 dimensions, the ones that represent the strongest signals. You throw the rest away.
So by discarding all that noise and keeping only the strongest signals, you're forcing the model to generalize. You're compressing that massive sparse space into a smaller, denser semantic space.
That compression smooths everything out. When car and truck frequently appear in documents related to one of those strong top dimensions, the SVD process maps both words close to that dimension. In the new, reduced space, the vectors for car and truck are now mathematically close together.
You've solved the synonymy problem.
You have. A search for car will now also retrieve documents that only mention trucks because their underlying conceptual representation is now the same.
And the applications went way beyond search, I assume.
They did. LSA was used for document clustering, for grouping similar documents even if they use different words. It was even used for cross-language information retrieval, where you could link documents in different languages based on a shared semantic structure.
So if it was so revolutionary, why wasn't LSA the final answer? What were its limitations?
Well, two big ones: computational cost and its statistical assumptions. SVD is a very heavy-duty process. Applying it to a matrix with tens of thousands of terms and hundreds of thousands of documents was computationally prohibitive for most people in the 90s and early 2000s.
So you couldn't just refresh your semantic map every day if you had a growing collection of documents.
No way. And there was a theoretical problem, too. LSA assumes that the data follows a certain kind of distribution, a Gaussian or normal distribution. But word counts don't work like that. They're discrete counts. That statistical mismatch led to some inaccuracies.
Which pushed the field towards probabilistic models. Instead of just looking at correlations, people started trying to model the generative process of the text itself.
Right. They started asking, how did this document come to be written in the first place?
And the first step in that direction was probabilistic latent semantic analysis, or PLSI.
PLSI modeled the generation process. First, a document picks a topic, and then based on that topic, it samples a word. It was a more statistically sound framework than LSA.
But it had one huge, fatal flaw that made it impractical for the real world.
It did. PLSI only modeled the topic mixtures for the documents it was trained on. So if you showed it a new unseen document, it had no way of assigning topics to it. It couldn't generalize.
So we've hit another wall. We need a model that can capture conceptual meaning like LSA, uses probabilistic methods like PLSI, but can also handle data it's never seen before.
And that challenge leads us directly to one of the most successful and enduring models of this entire era.
Latent Dirichlet allocation, or LDA. Introduced in 2003, this took the thinking from PLSI and made it work in the real world.
LDA is really the culmination of this whole period of statistical modeling. And the core idea behind it is just beautiful. It says that every document you read is a random mix of hidden topics, and every one of those topics is, in turn, a distribution over words.
The chef analogy works really well here, I think. A document is like a cake. It's made of ingredients, which are the words.
Right.
But the cake isn't just a random pile of ingredients. It's the result of combining distinct recipes, the tomics. Maybe it's 70% chocolate cake recipe and 30% vanilla cake recipe. LDA looks at the finished cake and works backward to figure out what the recipes were and what proportions were used.
That backward inference is the technical problem it solves. It doesn't need any labeled data. It discovers the topics and the proportions just by analyzing how words co-occur across all the documents.
So if words A, B, and C keep showing up together in the same documents over and over again, the model infers they probably belong to the same hidden topic.
Exactly.
So what was the key technical ingredient that let LDA generalize and solve that fatal flaw of PLSI?
It was the introduction of something from Bayesian statistics called the Dirichlet prior. Instead of explicitly modeling the topic mix for every single training document, the Dirichlet distribution treats the topic proportions as a random variable.
And what does that do for the model, conceptually?
It acts as a kind of smoothing mechanism. Conceptually, it encourages the final topic distributions to be sparse. This is great for two reasons. First, it helps the model generalize better because it's learning how topics are likely to be mixed in general, not just how they were mixed in the training set.
And the second reason?
It makes the results much more interpretable for a human. It ensures that most documents will focus heavily on just a few topics, not a tiny bit of all of them. And it allows the model to assign probabilities to new documents based on these general priors.
So after the model runs, you can look at, say, topic 17, see that it gives high probability to words like planet, star, gravity, and telescope, and you can immediately say, topic 17 is about astronomy.
You can. It reveals meaning from completely unorganized data. It allowed researchers to move beyond keyword matching to conceptual clustering on a scale that was just impossible before.
And this must have had a huge impact across different fields. What kind of insights did LDA unlock in the early 2000s?
The applications were immediate. In political science, for example, researchers used LDA to analyze legislative texts and debate transcripts. They could automatically track which topics like defense spending or labor laws were gaining or losing importance over time just by looking at the word patterns.
That's amazing. What about something much messier like social media?
It was a game changer there for event detection. When Twitter started becoming popular, LDA could be used on the stream of tweets. If a new cluster of words, say earthquake, rescue, shelter, suddenly spiked in volume, LDA could group them into a natural disaster topic and flag that a real-world event was happening.
I even saw it applied in crime science, which feels like a surprising use case.
It just shows how general the method is. Researchers would use LDA on news reports or public records to identify emerging crime patterns. They could categorize incidents into topics like financial fraud or cybersecurity, and then link those topics to geographic data to predict hotspots.
So we have this incredibly powerful model, LDA, but at its heart, it's still based on that original bag of words assumption, isn't it? It's still an unordered collection of words within the topics.
It is. The internal structure of LDA was still limited by that same lack of sequence knowledge, so researchers immediately started building extensions.
If LDA assumes all topics are static, that's a problem for data that evolves over time, like news.
Which led to things like the dynamic topic model, or DTM.
How did that work? How do you add time to a model like this?
DTM models the evolution of the topic distributions themselves. Instead of assuming the words in the technology topic are the same in 1980 and 2020, DTM links a topic structure of one time slice, say 1995, to the next, 1996.
So you could literally watch the technology topic shift from words like modem and disk drive in the 90s to words like cloud and algorithm in the 2010s.
Precisely. And while DTM fixed the time problem, that core BoW grammar problem was still there, which led to another key innovation, trying to combine syntax with semantics.
And that gets us to part of speech LDA, or POS LDA. How did they blend the grammatical role of a word with its topic?
POS LDA realized that a word's meaning depends not just on the overall topic, but also on its job in the sentence. Is it a noun, a verb, an adjective?
So the model doesn't just sample a word based on a topic. It samples a part of speech tag first, and then samples a word based on both the topic and the tag.
That's the mechanism, and it's incredibly sophisticated for the time. It lets you discover distributions that are specific to both the theme and the grammatical function. You start getting specific lists, like nouns used in legal texts or adjectives used to describe guilt.
That's a huge leap in how useful the results are.
And here's the really clever part. POS LDA basically solved the stop word problem automatically. All those common function words like the, of, in, they're essential for grammar, but meaningless for topics. By modeling their part of speech tags separately, the model naturally pushes all those words into syntactic-only classes that aren't tied to any semantic topic.
So the semantic topics are left much cleaner, focused only on the important content words, without anyone having to manually create a list of words to ignore.
Exactly. So by the mid-2000s, we've gone from a simple count in a bag to this intricate model that can track changing topics, filter its own noise, and even understand elements of grammar. It's a colossal journey built on statistics.
It's clear this whole classical era didn't just predate modern NLP. It created the vocabulary and the computational goals that modern systems are still trying to achieve.
First, we have to acknowledge the strengths these models still have. Speed is a huge one. You can extract TF-IDF features from a massive dataset in milliseconds. For some tasks, like basic document tagging or spam filtering, it's still a remarkably fast and effective baseline.
And even LDA is pretty fast on modern hardware compared to training a huge neural network from scratch, right?
Absolutely. The inference methods used for LDA were designed to be tractable approximations. So for just discovering features in a large text collection, these models are often much, much quicker.
But the real historical significance is how the failures of these models pointed the way forward. What was the central problem that really demanded a neural network solution?
It was that inability to really capture semantic meaning. The sparse vectors from BoW and TF-IDF created this huge, lonely space where related words like car and truck were miles apart mathematically.
And LSA and LDA tried to bridge that gap with statistics.
They did. And that whole effort, the move from sparse high-dimensional vectors to dense low-dimensional ones, is the direct conceptual ancestor of modern word embeddings, like word2vec.
So instead of needing the whole corpus to tell us that car and truck are related, word embeddings learn it from local context.
Exactly. A shallow neural network learns to predict the words that surround car and the words that surround truck. If they share the same neighbors like drive, engine, road, they get assigned dense vectors that are physically close together in this new semantic space.
It's a predictive contextual representation instead of a count-based one.
We moved from counting what words are there to modeling how words relate to their immediate neighbors.
And at the same time, the struggles of models like LDA to incorporate grammar and word order.
Foreshadowed the need for sequence-aware architectures.
Mm.
Classical models either ignored syntax or bolted it on as a complicated extra layer. This is why researchers started developing things like recurrent neural networks, or RNNs, and LSTMs.
Architectures that were specifically designed to read text word by word in order and remember what came before.
Finally allowing the machine to understand sequence and context in a truly dynamic way.
So the core mission from the classical era turned text into meaningful vectors, find hidden structure, handle sequences. It's the exact same mission as today's transformer models. They just do it with a much richer understanding of context.
It's a fantastic testament to iterative progress.
Yeah.
Every limitation of BoW led to TF-IDF, which led to LSA, which led to LDA, which highlighted the need for sequence and context, which led to the neural revolution. It's one long, unbroken chain.
What a fantastic journey, taking us from the simple act of counting words in a bag to modeling these complex, hidden topic distributions that really powered the first generation of intelligent text systems.
And when you connect this to the bigger picture, it just shows the amazing sophistication you can achieve with simple statistical rigor. These aren't just historical footnotes. They laid the intellectual and mathematical groundwork for everything we see in large language models today.
So what does this all mean for you, the person listening right now?
Well, next time you use a search engine, or you notice your phone accurately predicting the next word you're about to type, just remember that the underlying statistical drive, the need to find important words, cluster-related ideas, and turn language into a usable vector, it's all rooted in these elegant foundational ideas of BoW, TF-IDF, and LDA.
And here's where it gets really interesting. We spent this whole time talking about models that struggled with word order and focused on the document as a whole. But imagine a system that learns semantics only by looking at the tiny window of words right next to a target word.
A system that learns cat and dog are similar simply because they share the same neighbors, completely bypassing the need for huge matrices or document-level statistics.
That sequence-focused, dense representation, the birth of word embeddings, is the crucial shift we'll explore next time.
Thank you for joining us on this exploration of the classical era of natural language processing.